Okay, hello everyone. We're gonna get started again. Our next speaker is Omid Nohadani. Omid is the Director of AI and Data Science at Benefits Science Technology, developing optimization and machine learning solutions for managing and structuring risk in health plans. He has been an associate professor at Northwestern and Purdue universities. He received his PhD in physics from the University of Southern California, was a postdoctoral researcher at MIT, and became a research fellow at Harvard Medical School. Please welcome Omid.
All right, thank you, Catherine, for inviting me, and thank you all for being here, and thanks to the organizers to organizing this wonderful event. So Catherine asked me to speak a little bit about models and methods in general in machine learning, and I added the from data to decision to it to sort of give a little bit of my view as well as the overall landscape. I'm sure a lot of you are already very familiar with some of the things I will be talking about, but I want to sort of organize them in probably a little bit a different fashion. But I will also give a few examples of the projects that we were involved with and go from there. Okay, so the plan is to sort of cast the view that there are different ways, different paths to arrive at decisions using data, and that in that endeavor we may have actually objectives that may vary in time, and it would require us to adjust our strategy. So taking an adaptive approach is usually very useful. Now, somewhere in the middle, I will also talk about some guiding principles that I think would be very helpful to keep them in mind. At least those are the kind of lessons or the beliefs that I have developed over the years working on this. And I will try to intermix a bit of scientific insights that is well established, as well as my personal experience over some years that have lasted the test of time. So that's the plan for today. So let's start off with data. Geithner, a couple of years ago, they came up with, as the big discussion started around big data, they divided data into three types. They talked about the volume of the data, the velocity of the data, and the variety of the data. Now, with respect to volume, that's kind of easy to understand. It's about the depth or the breadth of the data. And it often goes hand in hand with how much of the data do we want to, how much more do we want to collect, or how much of it do we really want to discard. About velocity, the aspect that comes more and more to light is with, for example, data streams, right? So when we have some physical bandwidth, and the question is how fast or how frequent do we want to collect the data, sense the data, as well as store the data, as well as the protocols that are required to either communicate the data or process the data. And the last piece, or the third V that they mentioned, was variety, which is about the different types of formats. So the format can change from time to time. The structure may become incompatible as you go from one data set to the next one. And there might be also some inconsistencies with respect to the semantic of the data that we are exposed to. Now, I would like to add a fourth component to this, which unfortunately I couldn't find a word with V. And I would call it quality, right? So the quality of the data that we collect in time with respect is really critical. And earlier, Daisy nicely put it out that it is not just, the more data doesn't necessarily mean the better or the more powerful the outcome, but we really need to be very careful and cautious about the quality of the data we use, because if the quality is not there, the outcomes would also fail on the long run. So the three aspects that I would like to point out with respect to quality is whether or not we can maintain the consistency within the data, whether or not our data is actually complete as we receive it, and lastly, whether or not the data within itself has actually a certain integrity. Does it repeat itself over time? Now, there are a couple of solutions that have been proposed and are in use in our daily lives. With respect to the volume, obviously, storing data these days is really a cheap commodity, right? And we have these beautiful flexible databases, data lakes, where we can store the information. And we are getting more and more judicious about what we are collecting, what we are discarding. Sometimes we actually have an on-demand way of regenerating the data if we already know what we are looking for. And we also can outsource the data collection or the data storage fairly easily these days. With respect to velocity, the periodicity of the processing of the data is really of key importance, as well as the time to access. So that very much depends on how frequent is the decision, so the time to access becomes a key point. And if we have issues with high latency settings, then we can actually use this point-to-point routing to work around that problem. If we have decision cycles that are fast or slow, we can actually adjust the collection of the data. We can balance the data that comes in to that decision cycle. And in many cases, we actually may require near real-time data collection. If you think of traffic, if you think of these wearable devices where you instantly want to know what is my EKG, that's with respect to velocity. Now, with respect to a variety of the type of data that we may receive, if we identify a relationship within the data that is hidden and we manage to resolve it, that usually gives a big boost to get rid of some of the variety that seems as a signal, but it's not really there. There are nice standardized formats. For example, the standardized XML that was introduced some years back that actually made a big change to the industry. Or if you think of the music industry as MP3 was introduced, there were all these other formats out there, and MP3 brought in the redundancy and the error proofness. It revolutionized the music industry. If we have, in terms of acquisition of data, if we are collecting them, if we predefine, if we have these predefined adapters, then we can overcome this challenge. And metadata management is more and more playing a big role. If you think about YAML has been proposed many years ago, but now it's used across the field, that allows us to store or gather contextual information as well as some predefined features that are actually available in the data, and so on. And if we have data of different types, let's say media, documents, and so on, advanced indexing allows us to actually interconnect them with each other, so we can better manage the variety within the data. When it comes to quality, again, some folks are paying a very close attention to it, and some are not exposed to it at all. If we actually impose automated checks, for example, using checksums, that would be fantastic. In the earlier talk, you saw an example of matching where you have streams of data that may deviate with respect to names or date of birth. That would help. And sometimes you actually have missing data where you can use ML-based algorithms to do imputation and corrections to that. Now, this is on the data side. A similar view can be taken on decisions. So decisions typically are considered in 4 types. If you go all the way back to Blaise Pascal in the 17th century, he already proposed to look at if a certain action can take multiple different outcomes at different probabilities, that a rational decision maker should actually look at expected values, not just at each one of these actions. And so this is the notion of decision or choices under uncertainty. And they can be because the initial conditions are unknown, or there are some parameters that we still have to collect, and that can vary. Sometimes our assumptions are inadequate, and we need to take that into account. And lastly, the actual system that we are looking at to decide on might be stochastic, and we need to make a decision under that uncertainty. The second type of challenge or decisions that I want to list here is decisions that are actually depending on time, right? So it very much matters if I take the decision today or tomorrow. Think of the stock market, for example, right? And where the results of an action, it depends on the actual time that we take that into account. The third kind is something that's not as popular or as obvious, which is the decision dependence. So we may have a cascade or an echelon of different decisions, and the later decisions may heavily depend on what actually happened the day before and so on. Like, what decision have we taken that allows us to, or that manipulates or changes, alters the environment so that the following decisions have to be adopted accordingly. And the easiest way to think about it is really to think about these decisions in time. But even if the decisions are at the same time or coherent to each other, they might actually interact with each other, and that has to be taken into account. Now, these interactions are very tricky because they very quickly end up in this nonlinear dynamics. And if the models are not suited to adapt to this nonlinearity, you might end up with some decision, you think it's optimal, all the quality values are high. You go in reality, you try to implement it, it doesn't work, right? So that's a part that's sometimes overseen. And lastly, complex decisions are decisions that have, come from a different setting. They might have different limiting constraints that needs to be taken into account at the same time, resource constraints and so on. And they require a combination of decisions and aspects to be considered at the same time. So now that we have data and the decisions and these four kinds, well, as I'm sure everybody knows, we do need models and methods to start from one and arrive at the decisions, right? And obviously, it very much depends on if we are looking at data that exhibits a big variety, and we are interested in choices under uncertainty, we need a certain type of model, or if we are actually instead looking at time dependence and so on, right? So depending on what type of data we have and what type of decisions we want to arrive at, that's basically how ideally the model should be selected from, and not just based on, I have this model, let me collect my data, and then I try to find the right nail for my hammer to go after, right? So if you, in your endeavors, if you can connect these dots together, that would be the ideal way of progressing, right? To connect these dots together. So having said that, this is the usual direction that things go. And we know that we start with data, we collect, or we are given some data, and then you try to arrive at decisions. Now, quite often, you actually start at decisions. You have a problem, and what you want is collect the right data, right? And that task is often understudied and undervalued, and that's a whole other area that one can actually focus on to optimize, to improve the way the data, the type of data, as well as the quality of the data that is selected in order to arrive at the right points, okay? So I would like to make a few comments about models in general, because models are, ubiquitous and everywhere, and we have been discussing them today. So I have these three principles, or these three things that I strongly believe in that sometimes are overseen. So first, I believe that models in general are not real, right? So models are wonderful, or sometimes wonderful mathematical constructions in our minds or on paper, and we use them to essentially describe how the nature works, how the things that we observe are behaving, right? They don't have a real manifestation. And as a result, yes, if we are doing mathematics, or if we are doing any other fields of science, and we want to enhance our models, that's a great exercise. However, when it comes to solving the problem itself and taking decisions, it is very helpful to keep in mind that the simpler the model is, the more useful they end up to be, right? So there was a conversation earlier about neural networks. Like, those models are humongously complicated and very complex. And that complexity often comes at the price of usefulness. Second point that I want to make is, when we are interacting with nature, what we observe, we record as data, right? So we can really think about data as to be the closest reflection of the reality, right? We are not always able to grasp reality in its fullest. So what we use is whatever we can observe, we store them as data. Now, the third point is when we want to do decisions, or when we are talking about models, right? The decisions ultimately need to solve a real problem in the real world, right? So the best test of a model, in addition to its mathematical beauty, is whether or not that decision actually solves the problem or not, right? So if you want to measure two models side by side, the best test is, does it solve the problem, right, to the accuracy? So these are sort of the three pillars that I try to, or over time, I realize and I would like to share with you. So if we are looking at, and so now I'm getting a little bit more technical, starting light. So if we want to have an overview of the different types of machine learning methods that exist out there, I would divide them based on the type of learning that we can have. So the first type is the supervised learning, where we have labels on our data, and hallmark examples are classification, regression, backpropagation, and so on. And so simplified, or simply explained, we have a whole bunch of data in these two dimensions. We split them in training data and testing. And now we have labels that we have on the training data. And then we try to sort of infer our model from training into make the same split blue versus red on the test data. The second kind would be the unsupervised learning. So we have essentially the same story, but now we don't have labels on the training data, and we are trying to do the inference between them. And the classic examples are clustering, dimension reductions, and k-means, and so on. So this list, by the way, is not meant to be complete. It's just an overview. And then the third type is semi-supervised learning, which is essentially a mix of these two, where we have partial information on the labels, both on training and testing, and then we use regression, classification, and so on to sort of map between these two, right? So when we step back and look at the popular ML methods that exist out there to address the point of this talk, is one of the big methods is regression algorithms everybody is familiar with. So we have a bunch of data, and we assume, and this is a big point here, we do assume that there exists a linear correlation between the data. There is an underlying linearity in the nature of this data, and then we try to fit a linear model to this. We try to minimize the error, and then we are done with our model, right? So this is the linear or logistic regression. We may have instant-based algorithm when we have the same type of data, but we are interested in their proximity or their similarities. And then we find a centroid using k nearest neighbors, or some support vector machines to have a cutting plane dividing the data with each other. We may have decision trees, which we just discussed about earlier, right? Where we start at a particular point, and we start dividing the data into pieces, and we ask successive questions to go down the line. We may have clustering algorithms, where we basically have cluster 1 and cluster 2, and we try to separate them from each other. And lastly, there are the neural networks, the deep neural networks, and all the flavors in that family, where essentially we borrow the knowledge that we have about the biological nature of neural networks to build a pattern matching model, where we essentially try to learn from the past data to infer about future observations. And we can use convolutional neural networks. So we have some input, then we build these layers, and we try to optimize the impact on the input on these layers. Then we try to optimize some weights amongst these layers, and so on. So in order to actually compute an outcome that would be our prediction for the future, right? So that's the overall a short summary of these different type of methods that are out there. Now, for looking at, I've worked on most of these areas for a number of years, and looking at what really combines them, or what I would pick as my guiding principles going forward, is the following. So all of these models and all of these approaches are very useful in their own area, but all of them have also shortcomings. And the scientific community is trying to really push the envelope to enhance them more and more as we go along, right? So there are, in my view, three things that are consistently missing, and if we work towards them or we have them in our minds, we will be able to have both better models in the future as well as better decisions and successful outcomes. So the first one I label as robustness. And robustness comes, thank you, robustness comes in two ways. So one is the resilience of our outcome, the stability, the scalability over time, whether or not something breaks or not, right? The other one is that we want to actually protect against unforeseen uncertainties, right? For example, if you take iPhone, the new type of iPhones, they have this beautiful feature of portrait photos, right? When I hold it against my face, I can blur the background, and it does a fantastic job, very similar to high-end DSLRs. However, if I do the same thing with the face of a cat, it fails. Both are faces, right? It is trained very well on human faces, but as soon as I have a cat or a dog, it does fail. So that's a good example of robustness, where if our model are trained to be also working well outside their comfort zone, then we have a model that can actually last and deliver better solutions. The second kind, which was just discussed, is on interpretability and transparency. So if we have the ability to connect decisions to data and answer all the questions around why is this, and bring the outcomes closer to the way human decision makers proceed with their thoughts, then actually we have a way of having a successful product. And the second part is on fairness and representation, right? Very often we have certain demographics is lower represented in the way we collect the data. It doesn't mean that they don't exist at all in real life, right? We just don't have sufficient data on them. So if we train our model not respecting this shortcoming, then we may completely oversee that aspect of the challenge that we are trying to solve. And the third one is the desire to actually be more abstract. So if we design or if we enhance our models so that they're capable to solve a more abstract problem, this way our solutions are capable to address similarly natured problems in future. So if I design a product or a software or machine learning algorithm that can solve my today's problem, but I solve the problem, or my method is actually done in a way that it solves the problem on a more abstract level, I'm already prepared for future challenges coming my way. So that's the idea with respect to abstractability. So in short, if we try to follow these principles very early on, not afterwards as a patch, or, for example, robustness, one option that people use is sensitivity analysis. Sensitivity analysis is a post-design tool, right? After you have the design, you create 10,000 of it, you check which one is least sensitive, you select that. But it doesn't mean that you took uncertainty into account up front when you were designing it. And second, if we have a team, or if we as scientists, researchers, as product developers, we actually prepare ourselves in the way that we want to really advance the current methods and model techniques to achieve at least one of these aspirations, we are in a much better place. So instead of just taking a method that exists, applying it to the data, and reading the result, if we are able to advance those methods, we are in a much better place. So in the remaining minutes, I will give you two examples on the first two goals, robustness and interpretability. All right. So this is, imagine you have data in 2 dimensions. Imagine your data on your decision, you have some boundaries, and you have also some cone on top. And now what you want to do is you want to sort of minimize some misclassification, right? So this is the problem that you're trying to solve. So the optimal solution would be this point down here, right? Now, In real life, we actually may encounter that these constraints are not exactly as you think they are, but they're kind of blurred. We are uncertain here. So the true solution is actually somewhere out here, right? The true solution is somewhere out here. And as a result, what we have to do is we have to take this error into account and solve the problem. So in the last 15 to 20 years, a new methodology has been introduced by the name of robust optimization, where the paradigm is to take the best worst case solution as your guiding principle, right? So we try to find first the most adversarial outcome, and then we find the solution that acts best despite all of that error and the adversity, right? So if you think of this to be the response surface of a particular design, and again, the design space is two-dimensional, right? If you pick one point, then the cost function value would be this area here, right? However, if this point is not a point, but we are uncertain where we are measuring, so instead it's this disk here, the actual cost function is somewhere up here, right? And it performs completely different. So instead of finding the lowest possible point on this graph, we have to essentially think in terms of disks and try to fit the disk the lowest possible place we can, right? So these are the options. The yellow disk that you see is the nominal optimum, but the red disk that you see here, this is actually the robust solution. This is the disk that fits the lowest, even though it's a disk, not just a point, right? So that's the paradigm behind it. So we used this a while ago to look at a very classic statistical method called maximum likelihood estimation. We developed the robust version of it. So imagine you have the actual true data, but you don't know them because you measure, this is what you observe, right? And in your observation, you have some errors, right? So we assume that the true data follows some distribution, and these are classic assumptions. If you do standard maximum likelihood estimation, you're trying to find the parameter that maximizes this likelihood, right? In the robust sense, we do exactly the same thing, but now what we do is we do exactly the adversarial view. We look at the worst possible errors that we might make, and then we try to improve that worst case outcome, and it works pretty well. So this was an example where we used for cancer radiation therapy. So this would be the healthy tissue, and then in the center is the cancer tumor. Radiation comes in, and this is basically this technology is used in almost all cancerous tumors to treat. Now, the decisions heavily depend on the location of the tumor and how the distribution of the doses across the area. And so people are very interested in computing this correlation of those points. And what they use is they use past data of like that one physician or the hospital, and they track it over time to report. And so what we did was, let me just go to the result. So this was the metric that they would measure. It heavily depends on which physician, which sample, and which sample size, right? If you change the same metric for a different sample size on the same day, meaning if you just change the physician, the same measurement jumps up here, right? Significant change. If you would do the same exercise with the robust estimators that I just showed you, and you add even errors to the measurements, and this is the size of the error, right? I'm not going to get into the details. You can see for an enormous amount of errors, even if you purposely try to break the system, the robust estimators are below what would have just happened if you pick a different physician. Okay? So this is one example on how robustness can be injected into the decision making. On interpretability. So we just had a nice talk on the decision tree, so I'm not going to dig deeper. So we know that they are interpretable. Imagine we have the two-dimensional space, and we have a whole bunch of red circles. We have some blue squares, we have some red diamonds, and we have some blue triangles, right? So the shapes are features that we measure, but we don't know if we really need them or not. What we are trying to get is we try to separate blue versus red, right? So what we can do is we can create a split at around 35. That makes the first cut. Then we do the second split and the third split. With 3 splits only, we can now actually separate, or we can predict blue and red apart, right? And the way this looks on the decision tree or as an interpretation is very much the same way. Namely, we ask the first question, on the x direction or on the x dimension, is it more or less than 35, right? If it's more than 35, that means we are in this zone, it is red. That's a very simple question to ask, right? If it's less than 35, okay, is it more or less, is the y, right? Are we above or below 37, right? Again, if we are above 37, if we are in this region, then it must be blue. Otherwise, we ask the next question. Within 3 questions, you actually got to your solution, right? And very often, you may actually end up to be right around the done after the first question. That's another big advantage of this. And Daisy nicely put it together. These trees, for the longest time, had the big problem that the choice of the splits were myopic. You could do only one step at a time. And as a result, the outcomes were a little bit unstable. But now with these new methodologies to actually use optimization to overcome this, we actually can solve these problems in a very large scale. Okay? So 1 minute, perfect. I'm going to make it 3. Is that okay? All right. So I will give you guys a real world example on this, the way we have been doing things at Benefit Science. So this is about trying to predict the risk of a healthcare, of the health of a human, of a person in the US next year based on the insurance claims data of the previous year, right? So kind of a crude level of data, we have a ton of them, and we want to predict next year's expenses. Now, there are 2 aspects where this is really valuable. One is on the financial side, where we want to assess the risk, and obviously on the health, right? Because we want the people to be healthy, and if we know that something is coming up, we want to be mitigating it, improving the condition, or probably coming up with a strategy how to treat. Now, there are 4 entities that are actually benefiting from both of these pieces of information. It's the actual patient, it's the employer of the patient, and it's the underwriter and the provider, right? And they all have different objectives. So if I summarize this together, the value that we obtain is such that the patient predominantly cares about the health, employer underwriter, the insurance, they are worried about the risk, and the provider is interested in how to provide the care or mitigate the condition, right? The tools that exist out there are the following. So either you can specify some score about the overall cost of the patient. It's some aggregate of the cost for next year. You don't know why, and the underlying medical conditions remain unknown. Or it is specific to some particular degree. What is the probability that somebody has cancer next year, right? It's specifically for that condition. Now, the tools that we have developed, they can actually fit both boxes because they are interpretable and they are accurate. So we can actually predict the cost fairly accurately for next year, and we can tell the patient why. Here's an example. So what we observe is about 97% of people who were last year at low cost, most of them this year remain also at low cost. Some of them end up to actually costing more, right? And in terms of the high cost claimants, it's almost a split, right? Now, when we try to predict them, I'm going to speed up a little bit. When we try to predict them, we do a very good job. Essentially, 92% of the people, we are accurately predicting not to costing too much for next year. This is sort of the false positive where you see the red around it. We assume they are high claimants, but they're not, right? And we do an okay job in this regard. When we are looking at the high cost claimant, this is really the tough part to do. It's only 3% of the population. And as you can see, the portion of them that actually end up to be high claimants, we accurately almost always predict them to be correct, right? And the reason for that is, let me just allow me to jump over this. So this is the new claimants, and we can, for the new claimants, we know exactly for which conditions we predict well, and for which conditions we don't do that well. For departing claimants, we have all sorts of conditions where we do pretty well. So green is where we are doing well. And most of them are related to pregnancy. So we can nail it down where they come from. And there are some cases where we really have a low confidence. If you take a closer look, you see that most of them are accidents. So we don't do really that well on accidents, but that's an obvious case. Now, the last piece in terms of the actual high claimants, what we observe is that the list is very long, and we have a very, very high confidence of all of these conditions which are not present in the previous year, but it's actually new in the coming year. And we can predict them all in a very high accuracy and communicate with the patients, communicate with the providers to essentially come up with strategies with respect to that. Okay? I know I'm almost over my time, so I will close with a few statements on there are big promises, I think, with machine learning. There are some caveats we have to keep in mind: interpretability, robustness, and the abstractability. And the possibilities that are out there, some of which that I try to exemplify here are, there are ways to actually extract interpretability out of data and keep accuracy, and there are ways to make things more robust. Thank you.
We have time for a few questions.
So, thank you. Very, very excellent presentation. Had a question about, you said in the case, where you had disparate data sources, that you can overcome that through various types of indexing methods. Could you just elaborate on that a little bit?
Yeah, so these are, it very much depends on the type of data sources that you have. But modern technologies do exist where you can have, for example, multimedia, you can have movies, documents, data files, and so on. And you can maintain, again, the answer really depends on the actual problem. But there are techniques where you can actually index them, and as they change, you can relabel and keep the same database forward while they are still connected to each other. That used to not be the case.
Okay, thank you, Omid.
Thank you.